Fast vector search is useless if the index drops the right neighbors. FAISS recall tells you how much accuracy you traded for speed. You'll learn how the pieces fit into a workflow that finds exact neighbors and tests approximate recall against them. I'm Professor Pi, teaching AI foundations with simple Python. When you build a search system over embeddings, you usually pick an approximate nearest neighbor engine for speed. That speed can hide small but important errors. FAISS index recall evaluation lets you measure those errors so you can choose a setting that keeps results useful. Think of a recommendation API that must return the correct similar items most of the time. If the index is too aggressive, users see wrong results. If it is too conservative, latency and cost rise. Measuring recall bridges accuracy and performance with a number you can optimize. At its core, recall answers a simple practical question. Of the top items an exhaustive search would return, how many did the fast index actually find? We'll make a tiny exact baseline, run an approximate FAISS index, and compare the two. Turning that vague hunch about quality into a curve makes the trade-off concrete. The strength of this approach is isolating indexing errors and giving a tunable knob. The weakness is you need a trusted baseline and representative queries for the metric to mean anything. We will build a hands-on mini evaluation. It creates a small, obvious set of vectors so we can see where coarse bucketing makes mistakes. Then we compute exact neighbors to act as ground truth. Next, we run an approximate FAISS index, vary how many coarse buckets it inspects, and record recall. Finally, we pick the smallest setting that meets a recall target. This is the practical pattern you can apply to any embedding search. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now let us make the tiny data that will expose boundary errors. This snippet creates a tiny line of vectors that FAISS can index. Approximate search is easiest to judge when the data has an obvious shape. So XB is just 80 points laid out from left to right. The two query vectors in XQ sit near the middle, where a coarse approximate index can make a visible boundary mistake. K equals 2 means every search will ask for the two closest database vectors. The visible output confirms the data size and dimensionality before any index logic appears. With the data defined, we need a trusted answer key that never lies, even if it is slower. This example builds the answer key with FAISS before testing anything approximate. FAISS.IndexIVFFlat L2 does exhaustive L2 search, so it is slower at scale, but useful as a trusted baseline. After exact.add XB, the call to exact.search XQK returns distances and neighbor IDs for each query. Truth turns each row of IDs into a set, which makes recall scoring simple later. The output shows the exact neighbors that the approximate index must try to recover. Now, we can build a real approximate index and see where it misses. This code runs a real FAISS approximate index and scores it against truth. FAISS.IndexIVFFlat first uses quant to choose a coarse bucket, then searches only selected buckets instead of scanning all vectors. With an nprobe equals 1, each query checks just one coarse bucket, which is fast but can miss a neighbor just across the bucket boundary. The hits calculation counts how many approximate IDs overlap with the exact IDs. The output shows recall dropping below perfect, which makes the solid miss visible. Seeing a single setting is useful, but we want a full picture of the trade-off between speed and accuracy. This snippet turns a vague speed setting into a measurable FAISS recall curve. The loop changes nprobe, reruns ANN.search XQK, and scores each result against the exact truth. Increasing nprobe makes IndexIVFFlat inspect more coarse buckets, which usually improves recall while doing more search work. Decreasing it can be faster, but this example shows how it can hide true neighbors. The output gives a compact before and after score, so the trade-off is visible instead of guessed. Once you have that curve, you can pick a practical operating point automatically. This example finishes the mini evaluation by turning scores into a setting you can use. Target defines the minimum acceptable recall, and passing keeps only the nprobe values that reached it. Choosing min passing favors the smallest FAISS search setting that still meets the quality bar. Then, the code applies chosen back to ANN.nprobe and runs one final ANN.search XQK. The output shows the selected setting and confirms the final result shape, giving you a tiny repeatable baseline for tuning ANN accuracy. Applied to a real search service, the same steps hold. Replace the tiny XB and XQ with your production embeddings and a realistic query set. Compute exhaustive answers on a small validation slice. Sweep nprobe or the equivalent bucket stand parameter until you find the lightest setting that meets your recall requirement. That selected baseline then becomes part of your deployment tests. 3 clear takeaways. FAISS Index Recall Evaluation measures how often an approximate index returns the exact top neighbors. Use this when you need to balance latency and result quality on embedding search. Keep in mind, it depends on a representative query set and an exact baseline, so false confidence comes from poor validation data. One practical next step is to tune nprobe on your real validation embeddings and watch recall at your target threshold. Try raising nprobe until recall meets the bar. Then observe the latency change and pick the smallest nprobe that holds. That single knob often gives the largest practical improvement for IndexIVFFlat style indexes. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.